Okay, we're live. Welcome to week 4 of statistics. It's the last week of this unit. There's a bit of a review involved, but it's not really a review. We are going to cover box plots, which is these things like what I have right here behind me. And we're going to apply measures of center and measures of variability, which sounds like a review because we covered measures of center and measures of variability for the first 3 weeks. So now we're just going to practice using them. We're going to exercise those statistical muscles. Okay, it is still the Women's World Cup of Soccer, so I am wearing a national team jersey. There are less and less teams still alive. This time I managed to grab a jersey for a team that is still alive in the tournament as I'm recording this. But after this week I might not be able to do that anymore because I don't have that many national teams. There are a lot of teams involved in the knockout stages of the World Cup right now that I've never had the jersey for. It doesn't mean I'm rooting for England, but on the other hand, I know it would mean an awful lot to them if they could win. Mocha is upstairs and she's staying upstairs because we have a grandchild over, and I know if she were down here, she would be scratching at the door trying to get up there to where the action is. So I'm not going to be bringing her to the camera right now. And the weather is cloudy and gloomy, but it's still summer, at least it's summer. Okay, now, the box plot. This is the box plot. The box part is right here in the middle. What is this thing? It's a graph. And to build it, we use a lot of the statistical measures that we've actually been using already. We use the median. We use the median of the lower half of the data, the median of the upper half of the data, which we were using already in order to find the interquartile range. So if you're able to draw a box plot, it means you're able to find interquartile range and vice versa. We also use the minimum and maximum values, that's the least value and the greatest value in the data, which are the values we use when we find the range itself. So range, interquartile range, median, all of these are in a sense a review because we've been doing them before, as are minimum, maximum, Q1 and Q3. Q1 and Q3, the names are new. We had been referring to them as the median of the lower half of the data and the median of the upper half. I hadn't been calling them Q1 and Q3, but that is another way of calling them. Q1 is the median of the lower half of the data, Q3 is the median of the upper half, and we can call them the first quartile and the third quartile if we wish. Median can also be called Q2. It's an alternate name, it means the same thing. Okay, so in this box plot, which is sort of a fictional box plot. It doesn't have any meaning. I don't have data that goes with it. I just drew it. And I drew it from the homework pack that at least some of my students have access to. So if you have access to the homework pack from the website, this should be very equivalent to the box plot that's on page 1 of this lesson. And we're just going to identify all the key values. So the median of this data is 15. The minimum is 2. We can read this comfortably off the plot if the graph has been made neatly enough, and I did manage to just barely make it neatly enough, I think. The maximum is 20. That means we can find the range already, so I may as well, here's my spot for the range. If the maximum is 20 and the minimum is 2, the range is going to be 20 minus 2. So the range is 18 for this set of data. Then the Q1, the median of the first half, is 12. So I'll fill these in as well. There's the 2, there's the 20. The Q1, the median of the first half, is the 12. I hadn't really identified the median up till now, but the median is right here. It's at 15. And then Q3 is 16, the way I drew it. When I look at this one in the homework pack, I found this was drawn in a way that's a little ambiguous, and I wasn't sure if it's supposed to be 16 or 17, but since they're not actually asking any questions about it, I wasn't able to verify. So my eye was telling me that Q3 was located at 16 in this drawing, and that's the way I did it in my drawing. So therefore, the interquartile range is going to be 16 minus 12, which is 4. Okay, so what is this telling us about our data? We already know that the median is a measure of center. So we have found one of the measures of center already just by looking at this thing. We know the median is 15, it tells us something. We know the data ranges between 2 and 20, the range is 18. We know that the IQR is only 4 though. That's interesting. Some sets of data where the range is as big as 18 would have an interquartile range that was quite a bit larger than this. You would have bigger boxes. And since the range and the interquartile range are useful for us when we are trying to talk about variability, we learn a little bit about our data from that. A range of 18 is quite a lot of variability. But an interquartile range of only 4 is actually not very much variability. So what is that telling us? It's telling us that whatever this data is, the lowest number was a 2, which is a very low number. But that was unusual, that there's not too many of these very low numbers, and quickly, even in the first quartile, we get into double digits. The interquartile range being so much smaller tells us that the middle half of the data, that's what's in these boxes, the middle half of the data, the middle 50% of the data. The middle 50% of the data actually doesn't vary very much at all. It doesn't stretch too far away from the median. But the overall set of data does vary quite a lot. So when we're talking about measures of variability, which one's better? In this case, I find that the interquartile range is better because the range sort of is misleading. It tricks you into thinking that there's a lot of variability in the data, but when you look at that variability of the middle half of the data, you realize, no, it's not really that much. So having both is useful. It tells us something about the data. When we look at a box plot, we're basically looking at the shape of these 2 boxes in the middle and these 2 lines, which are often referred to as whiskers. Another name for the box plot is the box and whisker plot. It's also known as the quartile diagram. There are various names that are used, but the whiskers and the boxes together show us all of our data. And we draw it this way differently so that we use boxes for the middle half and whiskers for the outer 25% on the left side and 25% on the right side, because it helps us to see things like what we were talking about, that difference between interquartile range and range in this case. So we can see an awful lot from this data, even though we don't have access to the raw data. That's interesting. Sometimes you have a box plot, but you also have access to the raw data, so you can find out even more. But the box plot is a really quick way to find out a lot of good stuff. Median, Q1, Q3, minimum, maximum, range, interquartile range, they're all just jumping right out at you as soon as you look at that box plot. So even if I had a table with all the data right next to it that went with it, my eyes would be drawn to that box plot because I would be able to find out a lot of things very quickly. What doesn't show on here is the mean, and also the mode. Now the mode, you can't find out anything about the mode from this diagram. You would have to have the raw data to be able to find out the mode. The mean though, you can't find the mean just looking at the box plot. You won't know it exactly, but you can sort of make a good guess at where the mean is. The mean is a measure of center after all, like the median. So the mean is not going to be that far away from the median. I wouldn't want to say, I think the mean is 15. I don't have enough information for that. I don't have enough evidence. I wouldn't want to even say the mean is somewhere between 14 and 16. That's again, I wouldn't be able to say that for sure. But to say that the mean is likely to have landed inside the box, in between 12 and 16, I feel a little safer there. So I can't tell you what the mean is, but I can make a bit of an educated guess about what the mean is. And that's interesting. Even though we don't have access to it, we can still see information that helps us to understand roughly what it might be. The median is much more trustworthy right now, of course, because we know for sure the median is 15. The box plot shows us that for sure. So that's pretty good. I'm checking to see how well I'm doing for time. It's a pretty good bunch of information for an introductory discussion about what a box plot is. The next thing that I'm going to do is I'm going to put some data up on the chalkboard, and then I'm going to draw a box plot. So I'll erase, I'm not going to erase everything. I'll leave these labels up here because they're useful and I'll be able to use them when I'm making the box plot in the next example. I will erase the answers to the range in the interquartile range, but I'll leave those up as well. And I'm going to erase the entire box plot. What I'll do is I'll put the data on the chalkboard so we can see it. Now this first set of data, it is from the homework pack, so a student who has access to this doesn't have to take notes. But it is a small set of data. There are only 7 values. The smallest amount of data I would want to use in an introductory box plot is 7 values. If you have fewer than 7, it starts being kind of silly to even make a box plot. But a nice small number like 7 makes it easy to see what you're doing. So we have to use some of the stuff that we've learned in past lessons. We have, this data is not in order, so I'm going to write it right away without changing the order. We have 34, 50, 49 and 47, 48, 45, and another 48. Now one thing that's happened already is I can see my mode because I have the raw data. I have 2 48s, it's the only number that appears more than once, I think, double checking, yes. So the mode is 48, that's interesting. So sometimes when you are given the raw data, you can introduce the mode into the conversation. It becomes yet just another tool to use when you're doing a statistical analysis. Okay, so I already see the mode, but I want to reorder this data before I start trying to find something like the median. So 34 is the lowest value, cross that out. Then we have all these values in the 40s, and that is 45, 47. I'll cross both of those out. Both 48s, cross them out. Where are they? There they are. And the 49 and the 50, I managed to reorder my data without making a mistake using the crossing out method. And now I can see things a little better. Now, when you have 7 values, it's a really quick set of data to find the median and to find the Q1 and the Q3, the median of the lower half, the median of the upper half. Because it's an odd number, that's one of the things that makes it easier. Our middle value is 48. That is my median, but I'm going to call it Q2. And over here, I'll write Q2 in brackets next to median. So the median is 48. I may as well identify it over here. And since it's so fast to do so, I may as well identify my minimum and my maximum. So there's my min, call it min for short, the 34, and the max is the 50. So I have a 50 here and a 34 there. Now, because we have 7 values, the left half has 3 values. We don't count the median itself. And the middle of those 3, this time I'll use a square, is 45. That is my Q1. And the middle value of these 3 over here is the 49. That is my Q3. I apologize if you hear background noise. There is someone mowing a lawn about 12 feet that way. But it's only a little piece of lawn, so it won't last long. Okay, so I can draw my box plot now because I've identified the 5 key values that I need. So the Q1 is 45, the Q3 is 49. This is not very hard and it is kind of fun. Definitely do quite a lot of these, practice a lot, because as you get larger sets of data and you get some data that's more skewed to the right or skewed to the left, you end up with different shapes to your box plot. And different things happen when you're going through the steps. A student who doesn't practice enough doesn't see enough of those different things happening, and then is taken by surprise when they do happen. So now let's draw our box plot. I need to do a scaling. I'm going to draw a line. I'll actually use a ruler for this. I'm looking at my video, and everything does look a little crooked. That's about how I tilted the camera. But I'm not going to bother fiddling with it now. I'm just going to do my best from my perspective to draw what I think is this nice straight line. And I won't put it too low. Now I want to scale this so it includes all these numbers, 34 to 50. Actually, I'm going to take a look at the one that we have because the answer is actually given on this sheet that I'm looking at. And they have scaled between 30 and 50, so I'm going to do the same thing. And I was just saying I'm going to drop this, and then it came true, it dropped it. Okay, so how long is this? I'll do it in inches. It's about 25 inches we're going 1, 2, 3, 4, 5. I'll do about 6 inches in between. So I'll just say 6, 12, 18, and then the 24 is at the end. And then I'll put another little tick here and make it a little longer there. So now I can scale it the same way it is on this information sheet. So we have, going up by 5s, we have 30, 35, 40, 45, and 50. And now we can draw our box plot. As soon as we have the axis scale and make sure that it will fit all the numbers we have, we're able to start drawing the box plot. The max is 50, so it's going to be right there. I'm just going to put a little dot. Then the Q2, the median, very important, that's 48. It's quite high, the median. So the 48 is going to go here. Then the Q3 is 49. That's going to go here. And the Q1 is 45, which is here. Boy, this thing is definitely stretched out in a weird way. I didn't do that perfectly, but I won't bother erasing. And then the lowest value is 34, which is way over here. I'm going to put another little dot for that. And now I can complete my box. My box or boxes. You can see this as 2 little boxes that are next to each other, or one big box that happens to have a line through the middle. You can call it either way. And then we need our whiskers. We need our lines that connect that to the min and the max. Now I'm going to compare this to the one that was done on this sheet and realize, okay, I shouldn't be so surprised by the weird shape of it because it's actually matching the shape. So this is good because if you think that you know what your box plot should look like, you don't want to be trying to draw a box plot that looks the way you expect. You want to find the key values and let them show you how to draw your box plot. And then when it turns out to be a little bit weird shaped like this, you won't be surprised. You're able to trust it because you're able to trust your values and the calculations that you did to find them. I have actually completed building this box plot, and that wasn't too bad. I will finish off this example by identifying my range and my interquartile range. The range is 50 minus 34, which is 16. We have a range of 16 this time. The interquartile range is 49 minus 45, which is 4. Just a coincidence that we have an IQR of 4 with this example like we did with the first example I mentioned about. Okay, so again, we have some data that's stretched out a lot outside of the box. The middle, the 50% of the data is in the box. And this is another situation where when I'm trying to look at my data and understand things about it, I'm thinking that I have more confidence in the interquartile range as a measure of variability than I do in the range, because the range is very large, and it's because we have that data value 34 that's so different from the others. And you can see the effect that that 34 has on the box plot, the effect it has on the statistical analysis of the data. We're finished. We've made this. Okay, I'm going to do another one though, and I'm going to check my time. It does take quite a bit of time to do this, but it's worthwhile, and you don't want to have too few examples. You need to practice. So what I'll do is I'll erase again, but I'll leave these labels again so that we can do the same thing with another set of data. And the next set of data that we have, oh, by the way, I should be very remiss of me. I'm going to slow down. And so this set of data that I just did was the number of animal crackers in a snack-sized box. Well, in 7 snack-sized boxes. So we can see, okay, now that puts a little bit more of a context, that 34, they probably aren't supposed to only have 34. So something went a little wrong on the assembly line perhaps for that box of crackers. But most of the boxes of animal crackers have amounts that are pretty close to the median, which is 48. And that makes me remember, well, I want to put a title. And to me, Animal Crackers is a good title. I just look for a title that makes sense, that puts us into the context. It still doesn't tell us everything. If we tried to say animal crackers, number of animal crackers in a snack-sized box, the title starts getting a little bit too long, and we're trying to put all the information into the title. We know we're talking about animal crackers. That's a pretty good title. And then we can label this, and I would label this as number of crackers. Now that might have seemed kind of obvious to a lot of people who looked at the graph, and they might think it's not necessary, but maybe it meant something else. Maybe it was length in millimeters of the longest cracker in the box. Something like that. So number of crackers is a useful label as well. Now I'm going to erase and do another example, and our next example is number of hours a small candle will burn. Yes, you're going to get some variability with an example like that. Okay, that wants to fall. Let's do some erasing. I'll erase these values. I'll erase all the raw data and the box plot. After all that work, it's a good thing we have videos that we can go back and look at. And I'll erase the answers for the range and the IQR. Okay, I will need the ruler again, the long ruler, but I'm going to just put it aside for now. Let's start with the data. Again, the data is not given in order, so I'm going to give it in the random order that it is presented, and I'm going through the process of reordering it. We have number of hours, 9, 7, 11, 16. Am I writing too small? I think I am writing too small. I'm going to make it a little bigger. Whoa! I'm not doing very well with my chalk today. 9, where am I? 7, 11, 16, 11, 19, 9 again, and a 10. I hope I don't run out of room. 15, 14, 8, 12, 15, 14, 8, 12. I will just have enough room for the last value, which is another 15. Okay, mode. May as well find the mode. I see two 15s. Do we have any other value that appears more than once? 12, 8, 14, 10, 9, 19, 11, 16, 11, 7, 9. There are two 9s, there are two 11s, there are two 15s. So unless I am mistaken, there are three modes. And that's what happens when you have a tie for mode, is that you just have more than one mode. I see three modes here. Maybe I'll be able to verify that after I reorder it. Another reason reordering is useful is to help us find mode. So the one-digit numbers are going to be the smallest numbers, so I'm going to do those first. We have 7, and we have an 8. Cross those out. We have two 9s. Cross those out. 10. Only one of those. Two 11s. Crossed out the 11s. 12. There is no 13. 14. Only one 14. Two 15s and a 16. 15, 15, 16. 15, 15, 16. Aha! And 19. So this crossing out thing comes in handy. It stops us from making mistakes. But there's the other thing that we can do to avoid mistakes, which is count them. Sample size, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 13 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 values. Okay, I think I have not made a mistake. The sample size is 13. 13 is another number that's fairly convenient when you're trying to find a median. So let's do that. The minimum is going to be, oh, I'm double checking my mode. I said there were three modes, 9, 11, and 15, and now I feel even more sure that I was right. I don't see any other numbers that appear more than once. Even the mode is easier to see when you do this reordering. I don't need to be holding this right now. So I'm putting it down. Now, the median. When there are 13 values, the 7th value is going to be the median. Double check that in my mind. If it's the 7th value, there's 6 to the left of it, 6 to the right of it. 6 plus 6 is 12, plus that 7th value is 13. I am right. Okay, so it's the 7th value. 1, 2, 3, 4, 5, 6, 7. The 7th value is an 11. That is our Q2, otherwise known as our median. Then, to the left of that, there's an even number of values. We're not counting this middle value. So when there's an even number of values, the Q1, the median of the left half, is going to be the average of the two middle values, which are both 9s. So my Q3 is a 9. Sorry, my Q3. My Q1 is a 9. The teacher will go and correct his mistake. Stop saying Q3 when you mean Q1. There. Now, the two middle values, wow, if this keeps on happening, the two middle values on this side are 15s. So my Q3 is a 15. Isn't that interesting? This is just a coincidence, I'm sure, but we had those three modes. And the 9s gave me my Q1, the 15s gave me my Q3, and one of those 11s was my Q2. Interesting, but just a coincidence. Okay, so we know everything. Q3 is 15, I will write it down. The min and the max are so fast to find. They are 7 and they are 19. We're ready to draw our box plot, but I will still also give the range, which is 19 minus 7, which is 12, and the interquartile range, which is 15 minus 9, which is 6. Again, the interquartile range is smaller than the range, but not as much smaller as with the previous example. So in this case, I find my range isn't quite so misleading, and both the range and the interquartile range are giving me a good impression of what type of data I have. That's interesting, just being able to compare them, comparing these two measures of variability. Okay, now we can draw our box plot, but we need to draw an axis and scale it. Let's see how this was done. Again, 2, 3, 4, 5 numbers divided into 4 equal pieces. So I'll draw a line about 20 inches long because it's easy to divide that into 4 equal pieces. Now the equal pieces I'm talking about are not quartiles. They're just me scaling my axis, because when you scale you want it to be proportional, meaning you go up by the same amounts. So 20 inches, I can fit that here quite nicely. And I'll put little notches, no, not there, 5, 10, 15, and at the end, of course, I don't want a little notch there. And now I can scale that axis. We're going up by 5s again, 0, 5, 10, 15, 20. 0, 5, 10, 15, 20. Now, I think you can see that there's a lot of flexibility in how we do this. I could have drawn a much longer line and I could have gone up by 2s. I could have drawn a shorter line and gone up by 10s. And I still would be able to draw box plots. One of them would be much bigger, one of them would be much smaller, but all of them would be readable. All of them, the person who's looking at it afterwards would be able to pull out the information they need, so long as you do it neatly. Making a really skinny one like that, going up by 10s, I wouldn't really recommend that. It's hard to do it neatly when you make it too small. And usually we have to think about the size of the page that we're limited to. If we're using a regular page and it's in portrait position like this, then that helps us to decide how wide a line we want to draw. I use centimeters a lot, so I often draw lines that are 10 centimeters in length. And then when I am scaling, I put little notches at every centimeter. It's really easy if you have data that are, for instance, percentages. Numbers that are going to fall between 0 and 100. I didn't want to say range, because the range of the data isn't necessarily the same as the interval that you're using for your scaling. And that's happening here. We put 0 on this thing, but our lowest number is a 7. We're not using everything in this graph. I'm just going to call this candles so that I remember to put a title in. And then the label that makes sense down here is going to be number of hours. Reminder, number of hours that a candle burns. Does it say more? A small candle. Okay, I don't think we're talking about those little birthday cake candles, because I don't think you'll find too many of those that will burn for 19 hours. So, small candle. We have context for our data. Now, we just need to take all these values and put them on the graph. It is so fast and easy once you're prepared to do this. So the median is 11. I'm going to put a line at 11. The Q1 is 9. I'm putting a line there. I'm trying to do it neatly. The Q3 is 15. That's easier to do because I have this little notch right above 15 on my scaling. The minimum is 7. That's going to be here. Oh, I was drawing a line, but I don't want a line. I just want to put a dot there. And the maximum is 19, which is way over here close to the 20. I'll put a dot. And now I can complete my box drawing. Draw lines across the top to show the middle 50% of the data. My boxes are complete. Draw lines connecting the ends of those boxes to the min and the max, and my whiskers are complete. I have a completed box plot, and we can see it's a little different than the other one. I don't have the other one right in front of me right now, but you might. The other one was stretched out. It was skewed to the left. This one is a little bit skewed to the right, but not so much. It's more symmetrical than the first one. These are also concepts that we have been talking about in past lessons. So even with the box plot, we find ourselves using nearly everything that we've been talking about for the past 3 weeks. We have not talked about mean very much, but we are able to say, well, I think the mean is somewhere in this box, and because of the way the data is stretched out, I'm guessing that the mean is a little bit to the right of this median. So I'm able to make my educated guess about the mean. Because I have the data, I could actually find the mean. I could add all those numbers together and divide by 13, and I would find the mean. I won't do it right now, but I could. And I can find the mode. I did find the mode. So mean, median, mode are measures of center. Range, interquartile range are measures of variability. The only thing we haven't talked about in this week's lesson is the mean absolute deviation, which is also a measure of variability, and which we could find in this case because we have the raw data. Kind of need the raw data. You could make an estimate without the raw data by looking at the box plot, much as we did with the mean with a previous example, but you need the raw data if you want to actually calculate mean absolute deviation. Okay, so I have another example that's complete. I'm very happy with this. I nearly finished the first page of this, homework pack. Now we have a question where we're given a box plot and we're just being asked to identify these values. So I'm going to draw the box plot the best I can, the same one that's on here, and then we'll find the 5 values. I know this is going to seem easy to most students, but it is worthwhile to practice this. You want to ask questions forwards and backwards. That's the way I always say it. When you learn a concept, you find different ways to ask the same questions, different ways to exercise that same part of your brain. Okay, so I will reproduce that box plot, and I'll erase everything that I don't need right now, which is all the answers. I'll even keep that n there. I don't know if I'm going to need it. I'm going to erase these values. And like in our first example, we're going to have a box plot that doesn't have any context. Yeah, all it is a box plot. It doesn't have a title. It doesn't explain what it's about. And you can still read things about it, and that actually is useful to realize that you don't even necessarily have to look at the title or the label. You don't even have to look at what the data is about to be able to answer certain questions, mathematical, statistical questions about that data. Nope, I won't erase that little Q2 in brackets. I think that's still useful to remind the students that yes, Q2 is a new thing, but it isn't a new thing. It's the median. Q2 and the median are the same thing. Okay, now I'm going to draw this box plot, and again, I'm going to try to reproduce it the way it is on this sheet in case there are students who are looking at this sheet, so they don't have to go and try and draw it. So again, it was 5 numbers, 4 equal sized pieces. I'll do it with 20 inches again, or no, I'll juggle it up. I'll do it with 28 inches, so I'm going to make it bigger. So drawing a 28-inch line, dividing it into 5 equal pieces means putting a little notch at 7, 14, and 21. Then the scaling. This one's not starting at 0. This one is starting at 8 and going to 20. So 8 is here, 20 is there. Is it going up by 4s? 8, 12, 16. No. How is this going up? No, it's going up by 3s. 8, 11, 14, 17, 20. 8, 11, 14, 17, 20. Okay, so the scaling is done. No title, no label. I have to draw it. So I'm going to start drawing here. And the students are already saying, okay, I know something, I know what the minimum is. That's true. I'm going to stop drawing over here. I'm going to put my median right here. And then I'm going to put my Q1 here. I can complete this part of the box and this whisker, and I have to put my Q3 and I'm going to put it right there. Complete this other box, other part of the box if you will, and that whisker. We have a complete box and whisker plot / quartile diagram / box plot, and we can identify our minimum, our Q1, our Q2, our Q3, and our maximum. The Q2, the median is 14. There it is right there. The Q1 is going to be 12. The Q3 is going to be 16. The minimum is 11. The maximum is 18. Teacher double checks to make sure that he didn't make a mistake. Didn't make a mistake. We may as well give our range, which is going to be 18 minus 11, which is 7, and our interquartile range, which is 16 minus 12, which is 4. Yet another interquartile range of 4. Again, that is a coincidence. It's not always 4. But the interquartile range is not that different from the range. So again, we have a situation where we feel both of these measures of variability are trustworthy. They tell us something true about the data. Neither of them is misleading. Sample size? No idea. This is good. It's good this happens. It's good to stop and think and realize, well, if all you have is the box plot, you don't know the sample size. You have to have the raw data to know the sample size. I cannot answer that. Mean? I know it's not going to be very different from 14. I know it's likely to be somewhere between 12 and 16, but I can only make an educated guess as to the mean. Mode? No idea. For all I know, there are 300 data points that made this, and let's say 33 of them are 18s. The mode could be 18. If it was a dot plot, you'd have 18 with the dots going up past the ceiling over it. It could happen that you would have a weird set of data like that, and it would produce a box plot like this. So the box plot doesn't show us everything. Mean absolute deviation, we can make educated guesses about that as well, like we can with the mean, but we cannot exactly know it, not unless we have the raw data. How am I doing for time? These examples are taking me longer than I was expecting. So, but I still think it's a good thing. I like the examples. I like all 4 of the examples we've looked at. I think that this repetition is extremely good when students are learning box plots and learning how to apply measures of center and measures of variability. Where am I now? I am finished with this page, so I'm putting it aside. And with the amount of time I have used and have left, I have to decide what I want to do. I am talking about some data that's on the pages, and this is something I was doing last week. It's the same reason. I don't want students to have to spend too much time copying down examples, so I'm using things that are in a homework pack that students can get access to. So if you're stumbling on this video on YouTube and you realize you don't know where this homework pack is, I apologize to you, but I think we can still get something out of this video. And I'm going to see how the viewers of the video feel about it from the comments. Okay, we're being asked to answer questions based on our knowledge of box plots. So if I draw a box plot really quickly, we can do this. So I think I'm going to do that. What I'm going to do is I'm going to stop with this always finding all the same values, and instead I'm just going to answer the questions that are on this page. So I'll erase this stuff. Okay, so this box plot, and I'm not even going to use the ruler, I want this to be fast. So I'm drawing a line, and I'm scaling it 0, 2, 4, 6, 8, 10. I didn't do that too badly, actually. This is number of college applications amongst senior students. But I'll just say number of C app because I don't want to draw a long label, and I'll say college my title. Now to draw the box plot, my min is at 0. My max is at 9. My Q2, the median, is at 6. Then I have Q3 at 8, and I have Q1 at 4. I can complete my boxes. I can complete my whiskers. I have a complete box plot, and I can answer questions about it. What is the range? The range. Largest value 9, smallest value 0. 9 minus 0 is 0. The range is 9. I won't write down all these answers. I'll just answer the questions quickly. What is the median number of colleges? Median, that's my Q2. That's my median. It's 6. The median number of colleges applied to is 6. Very fast to answer questions using a box plot once you know what the values mean. What is the interquartile range of the number of college applications? 8 minus 4 is 4. The interquartile range is 4. That was fast. Which quartile represents the greatest spread in the data? Which quarter of these 4 pieces of the graph, whisker, box, box, whisker, represents the greatest spread in data? You just look for the one that's stretched out the most. The greatest spread in data is in this first quarter. Quartile 1, we could call it. Between 0 and 4, there's quite a spread. Here we only have a spread of 2, here we have a spread of 2, and here we have a spread of only 1. Very quick to answer this sort of question. Now, why is quartile 1 larger than quartile 4? I guess I kind of already answered that question. Because the variation of number of college applications of students in quartile 1 was a greater variation than in quartile 4 that had the smallest amount of variation. What about these two? Well, they're equal in size. So there is no difference. Well, there is no difference in the spread in these two. So greatest spread, tie for the medium amount of spread, smallest spread. You can see a lot in a box plot. And that's it for this box plot. I want to see, I think what I'm going to do is I'm going to stop with the box plots lesson, and I'm going to switch over to this other one, which is applying center and variability. I have to be careful which is the first page. Here's the first page. Now, I don't have very much time. I'm not going to be able to cover too much of this, but I'm able to do some of it. So applying center and variability, I think to juggle things and to get away from the box plot for a minute. In fact, none of the questions on these 2 pages have any box plots in them. I'm going to draw a histogram, but I'm going to have to draw it pretty quickly. So how quickly can this teacher draw a histogram? Maybe I could have drawn the histogram and put it up in the corner before the lesson, and then you wouldn't have to watch me draw. Okay, so this is tricky. I'm going to just do my best. So here's the base of it, and I'm going to draw a line here, not all the way. I'm going to leave a gap in the middle, and then the same size line on the top. I'm going to label these as 0, 5, and 10. I drew that rather small. Zero, 5, 10. And then I'm going to draw the bars of my histogram. So there's a bar in the middle, which is the tallest bar, and it's going up to 7. So I'm drawing it. That means I can finish this. Then the one to the left of it goes to 4. The one to the left of that only goes up to 1. So I guess I'll try and make my bars the same width. So I'll do that, and I'll waste a little bit of the space over here. This bar goes to 5, and the bar at the far end goes up to 2. So I'm sure in saying that, those values, I have answered some of the questions that are going to be asked about this histogram, because the student is being asked to read the histogram and answer some questions about it. What else is missing here? It looks a little messy, and one of the reasons it's messy is that we shade the bars in our histogram. So I'm going to do some shading. And then it becomes more clear where the bars are and where they aren't. Well, that sure looks like a histogram. Okay. height in inches of some students. I'll just write height of students. I'll write height of Stu for short. So we have someone named Stu and he has different heights. No, we have height of students, just giving some labels because I'm used to, as a teacher, being fussy and saying, wait, where's your label, where's your title? So if I'm not going to do it, that's not fair. Okay, and these are frequencies. I'll put freq for short. Now we can see what's going on. But I'll just answer the questions. And then if I think there's anything else that I'll point out about this histogram, I'll point it out afterwards. The shape of the data. This data is symmetrical. It is not perfectly symmetrical. This bar is a little bit bigger than this one, and this bar is also a little bit bigger than that one. But we would still want to call that symmetrical data. It's close enough to be considered symmetrical. What does that mean? It means that we think that the mean is the best measure of center for this data. And that was the next question. I'm glad I answered it. What's the best measure of variability? The best measure of variability is going to be mean absolute deviation in this case, but I don't have the raw data. So don't ask me to tell you what the mean absolute deviation is. Someone says the mean will fall between 50 and 54 inches. Oh, I forgot to put labels on the bottom. So this is really meaningless data. Okay, so my label is kind of in the way. This is 40 to 44. This is 45 to 49, and I know that on the video it's going to be hard to see these numbers, but I don't have much room. 50 to 54, 55 to 60, and 60 to 64. What is wrong with this diagram? That this should be a 59, not a 60, because we have a 60 here and we have a 60 there. We're putting this the person who's building the graph in the position of not knowing which bar to put a 60-inch tall student, that is a 5-foot tall student, into. So I'm going to correct the mistake right now, and I'm going to change this to 59. Makes a little bit more sense. Okay, so someone says the mean of the data will fall between 50 and 54 inches. That's right here in the middle, and I agree with that person. The mean is probably going to fall towards the center with any set of data. It should be falling towards the center because it's a measure of center. But in this case, we can trust that it will land in the center, that it's probably going to land in here because the data is symmetrical. So we're back to that again. When we ask what is the best measure of variability, it's almost like these questions could have been asked in the opposite order. Why did I think mean absolute deviation was the best measure of variability? Well, I think that's because the data is symmetrical. Again, so symmetry. We know that histograms are not the only graphs where you can see whether the data is symmetrical or not, but in this case, I think it's kind of cool that we're analyzing this data and I find myself talking about the symmetry so many times. And that's it for that. So there's an awful lot of drawing to answer only those questions. Can I see anything else in here that is interesting? Can I see the mode? No, I can see the modal class, right? So I know that the class that happened the most often was 50-54. That's interesting. That's an idea that we hadn't talked about earlier, the idea of mode versus modal class. We can't see the mode because we don't have the raw data. So these 7 students who fall between 50 and 54 inches, for all I know, all 7 of them were exactly 50 inches tall. But it could be that all 7 of them were 54 inches tall. And any of so many other combinations could happen. So if all 7 of them were 50 inches tall, then I would start thinking, okay, if someone were to tell me that about this data, I'd be able to say, okay, well, the mode's going to be 50 then. Then I would have enough information. But a modal class is still a useful thing, even if you don't know the true mode. So that was an interesting thing. Now the range, is the range 64 minus 40, is the range 24? Again, we don't really know because we don't have the raw data. And these students who fell into the 60 to 64 class, we may not have had a student who is 64 inches tall. We may not have had a student who is 40 inches tall. So all we can do is make an estimate of the range, which is going to be somewhere, at the biggest, it's going to be 64 minus 40, which is 24. The range, the largest the range of this data could be is 24. but it could also be as small as 16, which would be the 60 minus the 44. Interesting. So what can you find out and what can you not find out depending on whether you have access to the data, depending on what type of graph you're given and what type of information is in it, is a really good everlasting question for statistics as far as I can see. How am I doing for time? I have enough time to do another example. But which example do I want to do? That is the question. I think what I really feel like doing for this video is making up 2 examples to finish off with. And I'm going back to the box plot. I like to think about this idea of whether you can see the mean in a box plot, that educated guess about the mean. So what I'm going to do is I'm going to make 2 box plots, and I'm going to make one of them really simple, and then I'm going to deliberately stretch the data and skew the data in the other one and see what happens. So let's say my data for the easier box plot, easier, the more very straightforward box plot, is the numbers 1, 2, 3, 4, 5, 6, 7. Okay, I'm going to do this pretty quickly. This is our Q2. This is our Q1. This is our Q3. Our max is 7, our min is 1. We know an awful lot. We can draw our box plot. If I draw a line and I scale it, I can draw this. The min is 1. The max is 7. The Q2, the median, is 4. The Q1 is 2. The Q3 is 6. We have a very symmetrical box plot, and we're not surprised. What is the mean? I think a lot of the students will look at the data and tell me the mean is 4, but I'm going to prove that the mean is 4. Mean 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 over 7 values equals 3, 6, 10, 15, 21, 28 divided by 7 equals 4. The mean is 4, so the student who's looked at it and said, I think the mean has to be 4. Well, why did it have to be 4? Because the data is so perfectly balanced around it. It put me in a position where I kind of knew this was going to happen even before I proved it. So let's do another set of data and compare it to this. So I'm going to change the data a little bit. I'm going to start off the same way. 1, 2, 3, 4 are still going to be my first 4 data points, but now I'm going to stretch it out. I'm going to put a 6, a 9, and a 13 as the last data points. So doing the same thing. Q2 is 4. Q1 is 2. Same Q2 and same Q1 we had over here. But Q3 is going to be 9 with this data. The min is 1 again, but the max is now 13. We have to draw our axis for the box plot a little differently. I need to make sure the numbers from 1 to 13 will all show. So I'll start with 0. I'll put 14 over there. That means 7 should be right about here. And that means 3 and 4 are here. 10 and 11 are there. I can fill in the other numbers if I want, because it won't take very long. Okay, it's sloppy. I'm not using a ruler, but it'll be okay. Now, let's draw our box plot. We have a min at 1. We have a max at 13. So far it looks kind of the same. It's using up the whole scaling. Well, that's because of the scaling away. Our Q2 is 4. Our Q1 is 2, just like it was before. I can finish this part of my box plot. Our Q3 is over here at 9 though. Finish that box and draw my last whisker. So what I have done is I've drawn a box plot where the data is all stretched out on the right half. Now what's going to happen to the mean? What I have been saying when I'm making my educated guesses is, because this data is stretched out so far, it's going to drag the mean that way. And this data is not very symmetrical, and this data is going to be very symmetrical. So the mean and the median are both going to be very central. In fact, they are equal in this case. And when the data is symmetrical, we consider the mean to be the best measure. Since this data is not symmetrical, we're going to tend to find that the median is the best measure. That's our 4. So the mean, 0 plus 1 plus 2 plus 3, sorry for writing so small, but I have to, plus 4 plus 5 plus 6 plus 7. Well, I have to be more careful. There is no 5. Okay, after the 4 plus 6 plus 9 plus 13, we still have 7 data points. We're still dividing by 7. 0, no, 0. There is no 0. I have to be more careful. I have to slow down. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 6 is 16, plus 9 is 25, plus 13 is 38. 38 divided by 7. 35 divided by 7 would be 5, so it's 5 point something. 3 divided by 7 is going to be 5.2? No, 5.4. Okay, now I'm going to have to get out my calculator. And is this all fitting? I'm making sure that it's all fitting on the video, and it is. Okay, so 38 divided by 7. Did the teacher get it right? It is rounding to 5.4. It's 5.428, etc. I can call it 5.43 if I want. Okay, so I guess I was right. My educated guess was right. These bigger values and the way that the data was stretched out on the right side here dragged the mean in that direction and made the mean quite a bit bigger than the median. The median is still 4. The median is 4 here just like it is there. The middle value is 4 in both of them. So we're starting to see reasons why we consider the median to be the best measure of center when your data is not symmetrical. That's why I wanted to do these 2 little box plots so that I can compare those things. I find that kind of interesting. But can I always trust this? I don't want to trust this. That's just one example. If I want to experiment like this and see what would happen, I need to do more than one example. For instance, what I did here was I made this box stretched out, and I made this whisker on the same side also stretched out. What if I only stretched out one of them? What if I made up some data where the whisker was really long, but the box was the same size as this box? That's worth doing. It's worth creating a set of data and then finding your values and drawing your box plot and calculating and finding the actual mean and seeing, would that still drag the mean to the right? And then we can do other examples. We can try stretching both whiskers without stretching the boxes very much. We can try stretching both boxes without stretching the whiskers very much. And we can see all the different things that can happen. Making our own examples is a useful thing because we get to experiment and we get a stronger and stronger understanding of what is making all these values be what they are. What is making all of these measures of center, mean, median, mode, measures of variability, range, interquartile range, mean absolute deviation. What is making them what they are? What is making our answers happen? And then as we get used to doing that, we start feeling more and more comfortable with data itself and with our graphs. And we can feel a little bit more confidence when we're analyzing a situation. We can start thinking, you know what, in this situation, I think I'm going to go straight to mean absolute deviation. I want to see what's happening with mean absolute deviation because I feel comfortable enough about statistics so that I can look at my data and think, that's the question that I think will have an interesting answer. With that, I am going to end this week's video. I'm nearly at the end of an exact hour, so I'll try to end it. You know what? I'm going to try to end it so it's exactly an hour long. Now, the best way to use up the last few seconds would be if I could get Mocha down here, but I don't think I'll be able to get her down here that quickly because I closed 2 doors between here and where she is. I will mention that although the weather was very gloomy when I started this video, it's actually quite sunny right now. So I'm kind of happy that the video is ending because I have a swimming pool and I think I'm going to go and jump into it because it wasn't nice enough to jump into the pool at any point so far today, nor was it yesterday. What am I doing with time? Yakety yak, eh? So enjoy the rest of the Women's World Cup, and if you're visiting this video from the future and the World Cup soccer is long over, well then I guess you can just go and look at the results after the fact and analyze it. Ooh. You could take, interesting, I keep on mentioning the Women's World Cup of Soccer. We could take all sorts of information about goals scored, time on the field, etc. I went past my hour, so I screwed that up. And we could do statistical analyses with that. Statistics applies really well to sports. And it applies really well to anything that you enjoy that involves numbers. With that, I will say thank you for being my supercharged students this week. I'm happy that we got to the end of this unit, but I'm also happy to know that it's not the last time that I'm going to be teaching you some math, because there are so many topics that I will be getting into. The next topic I want to get into is some really basic arithmetic, the building blocks that allow students to understand a lot of these concepts, including fractions and decimals and percent. Yes, that's what I'm going to do next. Have a wonderful week, have a wonderful summer, and I guess I should stop talking. I'm starting to babble. Bye-bye.